Started. Hello, everyone, and welcome to our session, Fusion's High Stakes, Who Wins, Who Loses. My name is Jalen Lewis, and I am the events manager here at Peak and will also be your moderator today. I am joined by Mike Human, the founder and industry analyst for Ignition Research, along with Sean Walsh, the chief of marketing here at Peak, where they will be diving into what Fusion Energy will need from us to succeed. Before we get started, I have just a few housekeeping items. Questions will be answered via the Q&A chat following the session, and the webcast is being recorded. It will be made available following the session for you to rewatch or share with colleagues. This is a monthly series, so be sure to watch out for our October session. Without further ado, I will now pass it off to Mike Human to get our session started off for us today.
Thank you much, Jalen. As Jalen said, my name is Mike Human. I am the Chief Analyst of Ignition Research, also Editor-in-Chief of the Fusion Report. So why don't we go to the next slide? So when people talk about fusion or nuclear fission or any of the sorts of new energy sources that are coming about, it's really all about electricity. If you look at the demand that the EIA is forecasting by 2050, it's about 43,000 billion kilowatt hours of electricity. That's 57% higher than the demand was in 2022. There's also people who believe that the US EIA estimate or forecast significantly underestimates the actual growth that's going to happen in electricity, that may be close to double that number. A lot of that is due to EVs, and as one of the big things is AI data centers, which are expected to go up to about 40% by 2030. Renewable growth is also one thing where people are a little interested in. The EIA is forecasting renewable growth from 30% of worldwide electricity in 2022 to 50% in 2050. A lot of people think that's kind of aspirational. Certainly in the United States, where you're seeing a lot of pushback against both wind and even solar. The other expectation is that there will be continuing pressure to reduce the amount of coal that's consumed to produce electricity. A lot of the areas where you have the most coal consumption, India, China, places like that, our expectation is that will be pushed down probably by a 1% CAGR because of health and global warming concerns. As a result of that, you end up with this, what we call an electricity gap. You can see between the demand here and the actual electricity supplied, which is down here. That's a pretty large gap. It's almost 15 billion kilowatt hours of electricity that we don't have a source for by 2050. And just in case you think this problem is something you can let your grandkids worry about or your children, it's going to start being a problem in about 2030. So, from our perspective, fusion is probably the only logical source that's going to actually be able to fill this gap here. Next slide, please. So let's talk about fusion, kind of where the investments in fusion are and kind of what's happening along those lines. As most of you know, fusion today, if you look at commercial fusion, is being privately funded for the most part by VCs and other firms like that. But fusion has a long history of government funding. First fusion experiments were as long ago as 1932. They were about the same time they were doing fission experiments. First fusion ignition was in 1952. It was a bomb called Ivy Mike. That was a hydrogen bomb that was about 15 megatons worth of power. Pinch machines were starting to be pioneered in 1957. The UK's Zeta machine was one of the first ones. First tokamaks came about in about 1968 in Russia and were followed pretty much across the world. First laser fusion machine at Lawrence Livermore National Laboratories was 1976. That's almost 50 years ago. In all that time, it took until 2022 to actually break what's known as the engineering break-even, or Q equals 1. That happened in 2022 at Lawrence Livermore's National Ignition Facility. So that's 46 years after they first started building these things. Commercial fusion really took off in the 2010s because of the revolution in high temperature superconductor magnets. These allow much higher magnetic strength much denser and a lot less energy required to drive. If you look at today, and this graph kind of helps show you, there's about 20 companies today that are worldwide building fusion machines. And total private investment in fusion to date is about $9.77 billion. That's not including China, which is probably at least half to 2/3 of that number. And on an annual basis today is probably doing more than anywhere else in the world. Today, the forecast for the Western world's investment in fusion will be about $3 million in this year that will be added to this pot. So, you're looking at growing a number that's probably close to 11 or 12 billion dollars altogether. A lot of money. Next slide. So who are some of the big players in fusion? The interesting thing about this, we talk about this, $9.7 billion that's in there. Of that money, 8.5 billion went into 10 companies. They're 87% of all the funding, commercial funding in fusion. Of those, Commonwealth Fusion Systems, the number one company, has 30% of that money. They've got almost $3 billion. You look at the top four, which are Commonwealth, TAE, Helion, and Pacific Fusion. They almost have 2/3 of all the fusion energy capital. And this is, again, not counting China. But you really get to the point of saying, how many companies are there really going to be that end up producing fusion energy plants? It's not the 20 or so they're going after. It's probably a significantly smaller number. It's interesting when you think about the fact that to get Rivian, who's an electric vehicle manufacturer, into their first IPO took almost $5 billion. And that's a product that arguably is significantly easier to make than a fusion machine. So one can expect all these numbers to go up, and if you're not going to reach $1 billion at some point, you're probably not going to make it. Okay, next slide. One of the questions we get asked a lot is how long is it going to take to reach commercial fusion energy, or putting it another way, putting electrons on the grid from fusion. There's probably three big steps to this. One of them is hitting Q greater than 1 in a grid-like prototype. In other words, I'm going to build something that looks similar to what the grid product would be that can reach engineering break even. To date, there's only been one machine that's reached that, and that's NIF. There are a lot that are expected to hit that or get very close to that in the next 3 to 5 years. Spark is a machine that is being built by Commonwealth Fusion Systems. That's expected to achieve or beat break even by a significant amount. ITER, the machine that's being built by the International Consortium, is also expected to make it, though ITER probably will not be until the late 2030s. There are a couple other people that are building plants that are kind of the first of these two bullets. They're expected to come out before 2030 and eventually reach a Q greater than 1. The second challenge is obviously building this plant and having it run for an extended period of time. It's one thing to do one shot, as they call it. NIF is a good example of that. That doesn't turn into commercial power. You need something that can run for hours or days and work fine and not have to be completely rebuilt after the end of that. And there's many products that are being built on to do exactly that. They're expected to come online before 2030. The final challenge is building the first commercial plants. These are plants that you could build 5 or 10 or 20 or 50 or 100 or 1,000 of, over the course of decades. These are expected to really come on in the mid-2030s. The two big ones people talk about today are CFS's ARC plant that's being built in Virginia. They started to do groundbreaking there, and that is expected to come on before 2035. And Helion's Polaris in Washington. This is the plant that's supposed to produce electricity for Microsoft. Both of those will be able to run long-term and produce economically viable fusion. At least that's the goal. Okay, next slide, Jalen. So think about what it takes to get to those 3 milestones. As we talked about, capital is one of the biggest ones. Building one of these machines alone will probably cost more than $1 billion, depending on what technology is being used. So, companies that are under $1 billion are going to have a hard time. And there's a lot of push now to not only start getting investors involved, but also getting the utilities themselves and governments involved in paying some of this money. Government funding has grown extensively in a lot of countries, the US not being one of them, unfortunately. Our funding's been cut off over the past year to 2 years, and seeing that come back, I think, is going to be critical. One area where we are looking pretty good is a friendly regulatory environment. As you can imagine, if you look at nuclear fission, it takes 10 to 15 years to put the plant online. That's not going to get us anywhere by 2035, and certainly isn't going to give us the number of power plants that we need by 2050. Luckily, in the US and UK, we've said, hey, guess what? Fusion needs to be looked at more like a particle accelerator rather than a nuclear fission reactor. That clears out a lot of the red tape that you'd get otherwise. So that's a really positive thing. Supply chain, and my buddy Sean Walsh is going to talk about that in a little while. It's an area that that we need. You know, these fusion companies can't build everything they need. They can't build the magnets. They can't build the vacuum pumps. They can't build all the other things they need. There's a lot of new technology that goes into fusion. So we need a viable supply chain that's made up of non-adversarial countries that can help supply these goods to these fusion companies. Plant cost. If you think of a nuclear fission plant, that's roughly $6 billion to build one, just one. Fusion needs to get to the point where it has a similar or cheaper cost than that. Our guess, it probably needs to be about $5 million. And then you need to get the investments to fund the deployment of these plants. And the final one, this is the one that probably most people care about the most. How much is the electricity coming out of that plant? There's some different milestones depending where you're looking at. In Japan, I've heard it's close to $100 a megawatt hour. In the US, the guess is somewhere around 50. A lot of it depends on what the power availability is in certain areas. If you need power and you don't have it, you might pay even more than those amounts just to get that power. So, reaching a point where you can do it in a viable way that is not ridiculously expensive is critical. Last slide, I think. And this is an interesting quote from Scott Mercer. I thought it was a pretty good one. You think about fusion when it started and rockets when they started. They're about the same time in the 30s, 40s, 50s, just shortly after World War II. And Scott's quote, and I love this quote, is fusion isn't rocket science, because if it were, it would have been done in the 60s. It's a much harder problem. This is probably one of the hardest problems that mankind has taken on. And, it doesn't happen on a dime. I think we all know that. But I've seen the spark plants in Massachusetts. The Commonwealth is working. I've seen some of the other ones. There's the real people building real things today that are going to eventually reach the point that we need to actually have reliable, reasonably priced fusion power that actually is on the grid in the next 10 years. Thank you very much.
All right.
All right.
Thank you
Thanks,
so
Mike.
much, Mike. We will now be moving on to our Chief of Marketing, Sean Walsh, as he gets into being Captain Obvious.
Yeah, let's go one more. Thanks, Jalen. So I don't know if you remember this old campaign from the 90s, but it sort of struck me as an interesting juxtaposition for this conversation. So I'm going to be Captain Obvious in this. I'm probably not going to give you any deep, profound insights, but sometimes when you think about what we do on a daily basis, the habits that we have, the decisions we make, they tend to fall into a pattern. And one of the things you have to do in order to make your gym time effective, lose weight, save money, is you got to change those patterns. You've got to look at the obvious things, and in many cases, stop doing some of the obvious things, and then actually execute other obvious things. And that's kind of the gist of this section of the presentation. So our friends at the SCSP, the special counsel, God, I'm drawing a blank on the name, who look deeply at a lot of the fusion and other science and technology areas, put out an article that's linked below here over the past couple of weeks. It says China has spent 6.5 billion on fusion, to Mike's comment about the 9.7 billion that's been spent in the public sector around the rest of the globe. So think about that for a minute. When we talk about what does it take to get there, AI modeling is one of the top things. So we've seen China's advancements with DeepMind versus what we're seeing with ChatGPT and Perplexity and Claude AI, I'll say in Western countries. Capital. One of the things that China can do is bring virtually unlimited capital to this problem. They don't have to raise money. They can mandate this is what we're going to do. They're giving the land and facilities. They can enforce technology cooperation. And if the recent article in the Wall Street Journal is accurate, they plan to graduate 10,000 PhDs by 2030 focused on fusion and the derivative areas required for fusion energy. While I don't admire their system, nor do I ever want to live in it, I will say that there is a certain efficiency to it. And as a competitive approach, we have to look at this. At the end of the day, this boils down to one fundamental question. Is China going to win and dominate this market for the next century, or are allied nation countries going to do this? Because it is a fundamental race in both of those cases. I know sometimes those statements, when we're trying to not have as divisive a world, can be a little bit, they can contribute to some of those concerns. But this is a race. This is a competitive environment, and we have to acknowledge that. One of the other big advantages that China has is access to critical minerals because they don't have the same requirements that we do in terms of environmental protections and other sorts of things. They have virtually unlimited manufacturing capabilities and, again, the ability to mandate by edict the integration of those supply chains. And over again, we have seen where Western companies invent the technology, but then they shift the manufacturing to China. When that happens, IP is transferred. There's no way around it. Over my roughly 40 years in the IT space, I can tell you I've seen this happen dozens and dozens of times. You move the IP and you move the manufacturing there. You got to share the IP for them to know how to manufacture something. You can't do it otherwise. And as a result, they go from fast followers to market leaders because they're able to take all of the investment and work that's been done previously. So these are obvious statements. I think anyone who has worked in any of these fields understands this risk. So now the question is, how do we change that? How do we stop doing the things that are obvious we shouldn't do with the future of fusion energy and start to do the obvious things that we need to do in order to maintain our IP, our manufacturing base, and the competitive independence that we want in this market? Jalen? So, in the immortal words of Alanis Morissette, isn't it ironic? So, one of the first challenges we have in the West is getting enough power to build all the factories to build all the stuff for fusion. So Peak's experiencing this right now as we're in the process of building out our new capacitor film capabilities. One of our biggest challenges is getting commitment for the power we need to run that factory. So one of the things that, as we look at where do we need to beef up, to Mike's point about the power grid, is it's not just a question of we need to beef up power grid for electricity demand. If you don't have the electricity, you can't create the fusion infrastructure to drive national security and national interest, whatever your nation is. Then the other big thing is we need to figure out how we're going to cooperate because right now we're a multi-headed hydra. As Mike listed, there are, Mike, how many were there? 10 companies that have raised over $1 billion or something in that neighborhood?
There's 10 that have raised over $500 million. There's about 4 that are $1 billion or close to it.
And each of them are working on slightly different designs. Now, not that China doesn't have multiple designs going as well, but if we're going to succeed as an industry, we need to build an industry ecosystem. And that means we're going to have to support a small number of base platforms. And this is done in IT, this is done in telco. I'm sure it's done in many other industries that I don't have background in. But it all boils down to some degree of standards. is we have to get agreement that there are things that fusion companies need to make in order to protect their IP, be competitive, and lead their industries. And whether you look at gas power plants, you look at nuclear fission power plants, you look at EVs, there's this dividing line between this is what we're going to source from partners, this is what we're going to hold as our proprietary IP. And as a fusion industry, we need to start that conversation now because that puts you in the case of sole source risk. All of these VCs that are putting these billions of dollars in, they want exits, they want IPOs, they want M&A. And one of the things that creates business risk is having sole source. So the more that we can have diversity in the supply chain, the stronger our industry is going to be, and more importantly, the faster it can grow. So when we do this, this also helps solve the ironic problem of needing power in order to produce power. And at the very end of it is you got to have the base materials. And if we look at the new investments that were made by the DoD into MP materials, this is a perfect example. There's a couple of other investments like this that are being done that really start to highlight where public-private can come together. But these are the risks we need to solve in the rest of the world because China can solve these problems by edict. They control the capital system, they control the infrastructure, they control the eminent domain questions about power grids and using land. And right now, for better or worse, they are the producer of 80+% of most of the critical minerals required in order to make fusion work. Jalen? So the next big question is, we know we can build a bunch of individual machines. Now the question is, can we build thousands of them? Mike, in your charts, I believe you had, or in one of your previous reports, you mentioned that by 2050, if they're 1 gigawatt plants, we would need something on the order of 13 or 1,500 plants.
That's correct.
To 20%.
Yeah.
Now, a lot of these initial plants we're seeing are more in the 400 to 500 megawatt range, which means this number could be as high as 2,500 in order to get to that same level. And here's the irony. If you want to scale in 5 years, when you have the prototypes ready, you need to start the supply chain now. So while I can't speak for every other element of the supply chain, I can tell you that for the capacitor film required for the power side, there's a 2-year lead time just to get the machines. Then you've got another year of construction, manufacturing, tests, setup. So it's about 3 years just to get a capacitor film line and factory running here in the States. If demand goes up, that lead time can stretch. And we've seen that happen in transformers. We've seen that happen in other things just in the base power grid for traditional analog-based systems. So when you throw in all the new technology that is being developed for fusion, that challenge is going to get slightly more difficult. Jalen? And here's a great quote from Dave Kirkley at Helion. If you want to commercialize, build the supply chain before you need it. Because if you win the science race and lose the deployment race, you won't win. And the fact that the CEOs of fusion companies are thinking about this is very healthy. But we need to transition from that philosophical position into an open ecosystem that can support it. Now, I'm not talking about open source. What I am saying is understanding what people need built. So if you need 1 million capacitors to support 1,000 fusion machines, we better get to work today. And that's the type of question that this webcast is really trying to address. So one more, Jalen. So for this conversation, I'm going to make a few assumptions that just like we've seen in almost every other industry, there's going to be 3 to 5, I will say, standard or large market share players.
Winners.
winners are certainly the end, but I'm trying to be a little, ironically for Sean, I'm trying to be a bit more politically correct. Um, and think about 1,000, 2,000, 3,000 of these machines deployed over the next 20 years. In addition, they're going to need spare parts. They have consumables that they're going to need replenished. And if it takes 3 to 5 years to really scale that supply chain, plus the capital, plus the manufacturing setup and specifications, there is a ton of work to be done. And if we're going to succeed versus China, guys, we got to cooperate. All right, Jalen. So, what are the biggest things that we see from the peak side of the world? So, number one is we need to know what to build. So, in the IT world, I know that almost everything is going to go into a standard 19-inch rack. I know how much power is going to be available in that rack. I know what the chassis size is going to be. I know what materials are going to be. I know what cooling is going to be. And around that, you can start to plan products. Next, we need to make sure we have the raw materials. Mike, I'm going to draw a blank. What's the specific type of copper they need for HDS magnets?
Yeah, I think it's beryllium copper.
Yeah. So you got to make sure you got to have all those materials. In our case, we need capacitor grade polypropylene. Right now, no one in the U.S. manufactures that. That material is bought in Belgium and Brazil and Japan and other places. We need to be able to produce that here in the States. And I'm certain that if you look at the 100 plus members of the FIA, each of them have something on this raw material list. And that's certainly in their supply chain survey as well. Then you got to build factories. I can tell you as we're looking at this right now, it's a 2-year process, is kind of the most effective that you can get through. And the other big question is you got to have the power to run those factories. And then lastly, you got to have the machinery and train the human beings to do it. So these are really 5 monster challenges that we have to solve in the supply chain. And we need to work together. More than anything else, whether it's an IEEE standard, whether it's working through Greg Van Dyke and the FIA supply chain, as an industry, we need to come together and figure out where are we going to baseline these standards, where are we going to set up the partnerships to do this, and ensure that we're cooperating together because we all need this to win, to Mike's point. We all have to be winners in this in order for the vision of fusion energy in the future to be accomplished. Jalen? So this picture came from the FIA summit this year. On the left, you have Bob Bumgard, the CEO of CFS. On the right, you've I'm going to draw a blank on the senator's name from Virginia. He made the comment. He goes, "Look, I built my business on industry standards in the telco world. And that is what enabled us to scale quickly. So whether you look at how data centers are built, telco environments, computer servers, networking gear, all of these things have reference architectures. So whether you look at the Intel Developer Forum for servers, or you look at telco NEB standards, all of these things enable the industry to build new technology faster and know that when they build that new technology, it can be integrated, installed, deployed inside a set of industry standards. And I think this is one of the areas where we can make material progress and combat the edict-driven approach that China can deploy. Next. Critical minerals. We talked about this. The DoD recently made an investment in MP materials for getting some of the most important ones. And this is going to be a combination of things. We need the government participation. We need new regulatory parts. We don't want to destroy our environment, but yet we've got to find a new degree of flexibility to compete in the world. It is not that the materials don't necessarily always exist within allied nations, but how we partner to extract them, do that effectively and with an efficient manner, and do that with a cost-effective approach. is one of the biggest things that, as a nation and as partners, we need to work together to solve. Jalen? And this was interesting. Just this past week, Representative Miller and four other, a total of four U.S. House representatives, bipartisan, two Republicans, two Democrats, put forth the American Fusion Manufacturing Bill. This is exactly the type of action we're talking about. So they specifically call out what's required for magnets, the different types of metals required for the vessels. How do we build the right fuels for these? The power infrastructure. They specifically call out capacitor films and capacitor manufacturing. This is the type of action that we have to get through the House quickly and turn into law. And I think this is one of the areas where we'll have a tremendous champion in Secretary Wright. His degrees are in fusion engineering. He's a proponent of it. It lines up with the current administration strategy. And while I know there are many people who look at DC and see gridlock, I think this is one of the areas where we can all cooperate because this drives national security, it drives energy independence, and it drives jobs in the US as well and in allied nations, which I think everyone can appreciate. Yeah. And then the power conundrum. This is the piece of it takes power to make power. So what are the fastest sources to this? So it was interesting. Secretary Wright this week mentioned that, rapid deployment of solar continues to be a priority. Development of battery technology. If you look at the grants that have made by the DOE Loan Program Office, they continue to invest in that battery technology to put sustained power on the grid. And natural gas is definitely happening. The other part is you're seeing extension of the current coal plants, which will help keep the total power available up while we get fusion online. And again, we all know these things take a long time, but the biggest thing in order to scale fusion is going to be, ironically, old school power to create new power opportunities in the future. Jalen? And then when we think about where we need to go with this, the machinery involved. So again, I apologize for using our company as a reference, but the machines that we require in order to make capacitor film are manufactured in Germany. The lead times are anywhere from 2 to 3 years, depending upon when you order and how that is applied. We're building factories and sites in parallel. Then we got to get power, get it all together, get it configured, make sure that it's producing with high quality at high repetition. That's a 3-year process for us. For other manufacturers, it could be shorter. I'm certain for some it's longer. But we need all of these things to be synchronized and orchestrated in order to enable those fusion machine companies to scale rapidly. And this is something that I think our industry really needs to invest time in. Uh, we'll be talking about this on a panel next week at Seattle Fusion Week with Greg Van Dyke, who's the chairperson for the FIA supply chain, and James McAllister, sorry, butchered his last name there, from Lawrence Livermore, and Mike from Ignition Research. But when we think about getting to fusion, I guess the most cliche thing I can say is it's a team sport, and we all got to know the same playbook. Jalen? So, what do I think we should do right now? My personal opinion is I think the FIA supply chain has all the right players, and that can be a vehicle to start to discuss these standards and building things out and cooperation. I know there's been some other work in various organizations. I don't have a vested interest which way, but I think this may be the most centralized approach. VC partners, if you look at the people who are backing fusion energy, Sam Altman, Bill Gates, God, I'm drawing a blank. I apologize. The folks from Meta and other places, they have incredible leverage with this administration, and we need to get them driving that going forward. The DOE, I hate to say it, but squeaky wheels get the grease in politics and in business. And we need to really, really start an industry-wide extra outreach to them to enable the funding for this to go forward. Whether it's LPO, whether it's other research grants, I know we've done FIRE, we've done a number of other things, but relative scale to China, we got a long way to go. Next thing we need to do is sell the job creation capabilities of fusion. If you look at the scale of what this industry could be, this requires engineers, trades, it requires accountants, it requires everything that makes our economy go. And we need to make sure that people understand what a massive job creation engine this is, from the beginnings of the raw materials that go into the supply chain, that go into the fusion machines themselves, that go into expanding the power grid and all the line operations that then drive the overall economy and AI data centers and all the other things that we want. Next, we can use this as a bridge to mitigate energy cost. We know that that's going to be a driver for the economy. The more cost-effective energy is, the easier it is to scale the overall economy, achieve the visions we have for AI and many, many other things. And we've got to invest in education. This is going to take a lot of engineers. It's going to take a lot of line people. It's going to take a lot of folks that know the fusion industry in order to make this work. And we have a 3 to 5 year window here before this really hits the grid. Depending upon who you talk to, the last FIA fusion survey said 2035 was sort of the midpoint that most people agreed on. We're seeing numbers earlier than that from Helion, but we have 5 to 10 years to really make this investment and be the global leader in this new energy that will dominate for the next century. It's very simple. Whoever owns fusion will own energy production for the next century. Jalen? So that's the end of my prepared diatribe and pontification. So with that, let's move on to some Q&A.
All right. Thank you so much to both of y'all for your insights. As we are opening up our Q&A portion, there should be a survey that should pop up on your screen. If you don't mind, just taking a couple moments just to get that filled out, and then we will move on to our Q&A portion.
All right, let's see what we have here. If you're still inventing the first fusion machines, how can we define the supply chain standards? Mike, you've worked in IT for a long time. You want to take a first crack at that?
Yeah, it's a great question. I mean, if you think about, yes, there are a variety of different approaches to fusion. The biggest differences are really between magnetic confinement and inertial confinement, or lasers and such like that. But there's still a lot of pieces that are very common across all of these. You all need a vacuum. Fusion doesn't operate if it's not in a vacuum. So it means you need vacuum pumps. There's a lot of things like that. Magnets is another one. High energy power supplies, pulse power supplies, things like that are things that all these things need. Ways to handle, manage, and inject fuel into a reactor. These are all things that we can work on today if we understand roughly how big the machines are going to be, roughly how they operate. It's like Dell and HP don't make the same servers, nor does Huawei or anybody else, but yet they have a lot of similar parts, whether it's power supplies, whether it's cooling systems, whatever it is. So even though we haven't finalized the design of the first commercial machine, there's still a lot of opportunities to work on the supply chain in a way to build common parts, or at least mostly common parts that can be used across them.
Thank you, Mike.
All right.
Our second question is why should fusion companies agree to share their design info now when competitors could steal it?
So the issue here is not necessarily asking them to share their design info. It's asking them what is critical for their growth versus what can the supply chain do faster and more efficiently. If you look at virtually any industry, from automotive, from power grid, IT, telco, there is a wide ecosystem. And it's that wide ecosystem that drives innovation and it drives cost effectiveness. It drives competitive pricing. It drives scale in terms of available resources and eliminates the risk of sole source. So, yes, it's a bit self-serving as a member of the Fusion supply chain to make this statement, but it's been proven across virtually every industry. And there's an opportunity here for them to accelerate their time to market and to leverage the venture capital dollars that other companies have put in. Because if they don't have to invent, redesign, repackage technology, and someone else does that for them, that gives them cash and engineers and resources to spend on their biggest problems that only fusion companies can solve. So I think that's the motivation and the rationale behind it. I hope they embrace it, but that's my 2 cents worth. Mike, I don't know if you have anything else you'd add to that.
Yeah, it's a great point. I think I would also say go back and look at the Apollo program. That happened 60 years ago. Okay, the designs were they weren't quite open source, but they certainly are known. Nobody's still built another one. There's a lot of know-how that goes into building these things that isn't captured simply in design. I think that if you look at also a lot of the movement that a lot of the companies have done, and CFS is a great example of this, they publish their results of their testing so that they can get third-party validation of those. Not because they're looking to do it as a science experiment, but mostly so that their venture capitalists can say, okay, I get it. I understand that it works. Somebody else validated that it works. And that's an important part of, when you're making huge billion-dollar investments in stuff that is as hard as fusion is.
All right. Our third question comes from Timothy. As someone who has done research on the first wall survivability, I am curious as to why no one mentions this in their reporting. Does this mean that the problem is solved? I'm not aware of any solutions. Or does it mean that no one has gotten to this yet?
Well, Mike, since you're the guy that wrote the
Uh,
book, the article on First Wall, I'm going to let you.
I say I'll jump on that grenade. I'll be happy to do that. So it is definitely a hard problem, Timothy, no doubt about it. As I'm sure you know, a lot of people are looking at different solutions for this. Whether it's liquid metal containment walls, whether it's high neutron energy resistant materials. It's not solved yet today. There are a lot of people doing a lot of work on it, and I think it's one of these things that solving this problem clearly is very important for fusion. I think that it's in many senses one that doesn't scare a lot of people running the companies um, as much as some of the other things that they can't do. They know they're going to have to build first walls. They don't know who's going to build capacitor or vacuum pumps or things like that. So if you hear a lot of these guys talking, I've interviewed most of them. It's really focused on the supply chain, and believe it or not, people is the other one. So it's not to say first wall isn't important. It's not to say first wall isn't hard. It's to say it's a problem they feel that they have to have control of anyway, and it's not one of the areas they're worried about from that perspective. If that makes sense.
All right. Our next question is why do you think that China is not having the same problem that we are when it comes to supply chains?
Well, let's say I think there's a couple of different answers that we can give there. I'm going to give the pragmatic one, which is uh, they have leading supply of the critical materials. Many of the existing things that are in these environments, they have manufacturing space for. They do not have some of the same limitations on regulatory for building power that lets them scale manufacturing and do this. And they have the ability to fund research in different ways than we do here. So I think those things give them a bit of a scalability approach, or an acceleration model that many of the Western countries don't have. Um, and I think beside that, it is much as we have seen our current administration uh, make fossil fuels a priority, uh, the Chinese government has decided to make fusion a priority. So those are all contributing factors to, why I think they're doing fairly well in this so far. So that helps eliminate a lot of things. Policy drives behavior. And because they have that unified approach that then drives their supply chain. The other part of it is that they can't say no. Uh, that's the other part to this is they can't decide they want to go do something else if Beijing tells them thou shalt make this happen and enable. So you've got to look at both sides of that equation. They have the manufacturing capability, the materials, the policy set that way, and a very big stick to wield in enforcing compliance.
And the other piece I'd say is remember from the late 20th century to just recently, we taught the Chinese how to be our supply chain for almost everything in the high tech world. They built it. They got really good at it. They're very good at it. And now they've got people that are actually, as Sean said, ready to move from being first followers or fast followers to, innovators. And that really, you've been doing the same thing for 30 or 40 years and you get really good at it, which they have, it gives you a big advantage.
Mm-hmm.
Our next question is what action is the advantage to fusion companies for taking the risk of building standards?
Well, this kind of is back to the other one about the supply chain is its scale, it's maximizing investment. It should lower cost. Bob Bumgard in one of his blogs talked about an objective for fusion to be effective. It had to get to $50 per kilowatt hour, if I recall correctly. Um, when you have competition, when you have multiple suppliers, that will help you lower your cost. It'll also make sure that you don't have shortages of supply, and it will allow that supply chain to be able to invest in innovation to continue to drive cost savings as we go forward. Because at the end of the day, for all of the benefits of fusion in terms of its efficiency, its low risk, with limited radiation risks, with its clean energy footprint, all those things that are beneficial, it's also got to be cost effective. And I think that is the biggest motivator in all of this is that for all these fusion companies to succeed, they ultimately need to be cost effective.
All right, as we were coming up on our time, we just have one last question for y'all. It sounded like you wanted to see an open source fusion.
Yeah, I've actually had people mention this in the past. It is about open sourcing fusion. Um, I can tell you as someone who has built technology in standards environments, you do not give up your IP. What you do is you enable the rest of the supply chain to service your needs. And the good news is that there are 100 plus companies in the FIA that don't make fusion machines, or I think it's 100 plus. I'm sure someone will correct me if I've misstated that. But there is a large number of folks that want to service this industry, that believe in it deeply and want to see it happen. They have raised money on that conviction that it's going to happen and have a survival requirement to make it happen. But more importantly, it makes sense from a business perspective. They want to protect their IP. They want you to have your IP. And what you need to be able to do is understand where do those products interface. And if you can agree on those things, you create speed of delivery and speed of scale.
Thank you. That will conclude our webinar on Fusion's high stakes, who wins, who loses for today. If you have any questions that were not answered, we will reach out to you directly with those answers, or please reach out to meet with and watch Sean Walsh in action as he dives more into this discussion during his presentation at Seattle Fusion Week this upcoming Monday, the 29th. Thank you to all of our viewers for joining us today, and thank you both to Mike Human and Sean Walsh for their talks. If you're interested in joining us again, please pay attention to your inbox where you will receive the slides from today, collateral from our discussion, and information about our next webinar. If you have any topics that you would like to see, or if you would like to even join on and be a panelist, please reach out to whatsnext@peaknano.com. Thank you again for attending, and please stay connected through the following platforms. We would love to keep up with you and make sure that we are all up to date. Thank you, everybody.
Thanks, guys.
Thank you.
Bye.